Where do the special angles on the unit circle come from? And honestly, there's a pretty good geometrical demonstration that you can show where they come from. And the first one is to look at isosceles. I'm gonna be surprised if I spelled that right. An isosceles triangle, the triangle where all the sides are the same length. And so I'll do my best to sketch kind of what that looks like. And I should probably scale this up a little bit. Let's back that up a little bit. Let's make this triangle much bigger. So the only thing you need to know is that the sides of this triangle are all the same length. And just for the sake of making the problem easy, you can make all of those lengths 1 if you want. And there's something neat about triangles is that if these sides are the same, the angles have to be 2. And this isn't a geometry class, so I'm not going to reason through and prove that for you. But the angle across each of these sides should be the same. And if all 3 of these angles are the same, we'll call it let's call it theta. Then 3 of those thetas together should equal 180 degrees, which lets you know that these are 60-degree angles. And that might even be part of your definition of what an isosceles triangle is. It may be true, but you know that each of these are 60 degrees. Now, where I'm going to deviate a little bit is I'm going to drop something called a perpendicular. So, P-E-R-P-E-N-D-I-C-U, no. Perpendicular? That looks right. From one of these angles. So if you just grab any one of these vertexes, and you drop a perpendicular, that means it's a line from that vertex to the other side that makes a right angle, then all of a sudden you have made 2 right triangles, right? So if this is a right angle, because I made it that way, that's the way that I constructed it, this is 60 degrees, and 90 plus 60 is 150. We only need 30 degrees to get the rest of the angles in this triangle. So we know that this, oops, stop doing that. It's 30 degrees. And so the cool thing about that is you can use a lot more geometry if you'd like. But you could also show that these 2 sides, these right triangles, now have to be 1/2. Because if the length used to be 1 and you drop it 30 degrees, it's got half the angle pointing at it. It means it should be half the size. Half of 1, 1/2. And so now you can get all of these special angles, well, not all of them, but a lot of them from here. For example, if I want to know what is the sine of 60 degrees, then the sine of 60 degrees is going to be the opposite over the hypotenuse, SOHCAHTOA type stuff. But the question is, what is the length of this perpendicular that I've dropped, the height of that? And the answer is, well, it's going to be 1/2 squared plus that h squared is equal to 1 squared. Good old Pythagorean theorem. Your a squared plus b squared is c squared. So we have 1/4 plus h squared is 1, which means h squared is equal to 3/4, which means h is going to be plus or minus, but for the sake of the lengths of a triangle, I'm only ever going to consider the positive version. The square root of 3 over the square root of 2, which is 4. Oops, square root of 4, which is 2. Said that all kinds of backwards. So this side right here is the square root of 3 over 2. And so sine of 60 degrees, opposite over hypotenuse, is the square root of 3 over 2 over 1. Square root of 3 over 2 over 1, which is just the square root of 3 over 2. Similarly, your cosine of 60 degrees is 1/2, because it's going to be the adjacent 1/2 over the 1. 1/2 divided by 1 is still 1/2. You can also turn the triangle the other way, and you can start asking about 30 degrees. The sine of 30 degrees, running out of space here though, sine of 30 would be opposite over hypotenuse. That's your 1/2. And the cosine of 30 degrees would be your adjacent over your hypotenuse, or your root 3 over 2. So there are your special angles for 60 and 30, which aren't so bad. The only other angle that we look at is the 45, and you can do this in a very similar way. What you end up having to do is not drawing an isosceles triangle, but drawing a right triangle whose legs are equal to 1. Is this going to erase the whole segment? It is. That's okay. I'll redraw it. So these legs are equal to 1, and this is a right triangle. So it's not quite isosceles, but it's similar because this is missing the hypotenuse. And using our Pythagorean theorem again, 1 squared plus 1 squared is going to be equal to this c squared over here, because this is c. You see that 1 squared is 1, plus 1 squared is 1, and 1 plus 1 is 2. So you c squared is equal to 2, which means c is square root of 2, plus or minus, but just talking about side lengths here, so you get the square root of 2. And so if you pick either one of these angles, and you know what they are, they have to be the same. Right? If I call this thing theta, like I did before, then theta plus that 90 degrees should be your 180 degrees that are in the triangle. Which means two of these thetas are 90 degrees, which means one of the thetas are 45 degrees. So these are where the 45 degree angles come from. And if I ask you, hey, what's the sine of 45 degrees? Well, you go sine is opposite over hypotenuse. So that is the 1 over the square root of 2, which is true. But we like to rationalize numbers just to make them look a little nicer. And so if I just grab another color here and multiply this by the square root of 2 over the square root of 2, then I'm allowed to do that because I'm multiplying by 1. And multiplying by 1 doesn't change a number. 1 times root 2 is root 2, but root 2 times root 2 is just 2. So that's where you get your sine. And guess what? Nice symmetry here. If you ask about the cosine of 45 degrees, that would be the adjacent over the hypotenuse, which is also square root of 2 over 2. So that is a way that we can get both the sine and cosine of 30, 45, and 60 just by using a little bit of symmetry and some triangles.